Check. Cool. Hey, everyone. Thanks. Pretty excited to be here. This is my third or fourth time speaking at BSides, so thank you all for coming. My name is McIntyre, and we're going to talk about the runtime manipulation of some processes in OS X from a post-exploitation environment, specifically through Meterpreter. So I'm going to talk about some of the features that I've added in, some of the issues I had to overcome, and ultimately give a demonstration on what we can do with it. All right, so this is what we're going to talk a bit about real quick. We're just going to do a real brief overview of who I am, not the exciting part. Then we're going to talk about Python and C types, because this is all implemented in Python. If you've spoken with me before, seen my previous presentations, I am a huge fan of Python. So this is all implemented in the Python interpreter using the C types library. So we're going to do a real quick overview of that, because that's a very integral part to the low-level stuff that we're actually doing to change these processes and run them at runtime. We're going to talk about how we actually use that to integrate into Meterpreter, and how Railgun actually works. So if you've never used Railgun before, or actually have never heard of Railgun before, chances are pretty good that you've actually used it and just didn't quite know you were using it. It's a low-level functionality that's implemented within Meterpreter as one of the extensions, and so we're going to talk about how that's actually used and what benefits and advantages that has over doing some things like another way. Everything we're going to talk about here, like you could do it another way, but this way is going to be a little bit cleaner, so we're going to talk about why. Finally, we're actually going to talk about using like the lib Objective-C, and we're going to do a real-world example where we're going to inject and execute an Apple script into our victim Mac here, and we're going to run that from within memory. So if you have any type of like a post-exploitation Apple scripts that you have, you're obviously not going to want to have those like written to disk. You're going to have antivirus that's going to gobble those up. So we're going to show how you can do that without actually writing to disk. So real quick, my name is Spencer McIntyre. I work at SecureState. Bunch of us here at SecureState. I do research development, special projects. I'm a huge fan of open source. I contribute a lot to the Metasploit project, and I do a lot of other projects like in Python and things. So that's enough about me. All right, so Railgun, or this is where the pew 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 comes in. I can never say Railgun without hearing that like pew 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 in my head, because that is just such a fantastic name, Railgun. It sounds amazing. So why do we care, or why do we want to do this through Railgun? So the number one reason is stealth. It's all about the stealth. Flexibility, yes, but it's primarily the stealth. As a penetration tester, I've never spoken to a penetration tester that was like, you know what, I really want to get caught today. Like, I really want antivirus to like gobble up and like stomp out all my payloads, everything I'm uploading. Nobody wants that. So what Railgun does is Railgun allows us to interact with foreign functions similar to C types, but allows us to do it remotely through Metasploit. So we can call these OS APIs without writing anything to disk. Alternatively, if you were going to do this without Railgun, on Windows or like OS X, Linux, some of the problems that you would run into is basically you would end up like writing out a C file, uploading that C file, compiling it, and then running it from there, and that's not really going to be any good. In addition to having to like touch disk, if that is the approach that you're going to take, you're also starting a brand new process. So if anyone is like listing out the processes and it's running for any amount of time or anything like that, they're going to notice that like, hey, this process doesn't really belong. It looks kind of fishy. Fair warning though, one of the drawbacks that Railgun does have is that it's a lot slower. In order to do this, there's a lot of I/O back and forth between Metasploit, the controlling, and the actual Meterpreter host. So it's a little bit slower, but it's going to be a lot more stealthy, and you're not going to have to write anything out to disk, things along those lines. So this is how Railgun actually works. Over there on the far right is how a actual real Railgun works, but I couldn't actually find anyone that had made a image of how the software version works. So I'm going to go ahead and explain that out. So like I had mentioned, it's a foreign function interface similar to C types, but it allows it to be done remotely through Metasploit. So Metasploit has a whole bunch of definitions for the various library files that you might want to use, and you're probably familiar with these from like a Windows perspective. You have like ones for user 32, kernel 32, ADB API, all those ones there. And these definition files have the list of all the functions that are exported and the different parameters that they take. And we use this information to construct our request to Railgun, which is then going to execute those functions on our behalf, and it's going to pass in the parameters that we specified. It's going to return the information necessary for us. It's going to give us all of that, and it's going to happen all of that in memory. in the case where you're running library calls, it's also gonna handle like the loading of the DLL into memory. All of that stuff gets handled for you, so you don't have to worry about doing that. You don't have to write up a C file, dynamically load something in, nothing like that. It takes all of that for you. So one of the big things that comes out at this level, because we're interfacing with the C API, is that we need to know the direction of parameters. Microsoft does a really good job with documenting the direction of parameters. Some of the other libraries, since I ported this over to Linux and OS X, not such a great job as far as documenting the direction. What the direction means is that a lot of information is being passed in as pointers, and so we need to know, is the function going to read from this pointer? Is it both going to read and write to this pointer, or is it just going to write information to this pointer? So if we're calling a function, a good example would be like DNS query. That takes a out parameter where we give it a pointer and we say, hey, please put your information here. And in this case, that's out because it's going to write that data there, and we don't necessarily have to initialize anything and pass it in. But with Railgun, we can do both of those. But it breaks out all the parameters that you have into these three types: these in, out, and out. And then it copies all of those onto into the memory of the process that's going to run the Railgun call for us, which is that process that Meterpreter is also running in. And then from there, it passes in the references to each one of those blocks. And then for the out and the in-out, it's going to return that data back to us. So at a very low level, that's what it's doing, but that's how it allows us to pass in like opaque data structures for some of these larger functions. DNS query would be a good example. So, like I had mentioned, if you hadn't heard of Railgun, chances are really high you've probably used it. If you've used most of the post Windows modules and a few of the local exploit modules, Railgun is how a lot of those leverage the functionality of Railgun to make the calls that they need to make in order to get that information. Some of the Windows local exploits use Railgun to call NT device IO control file, so at that point they can pass in the IOCTLs and those routines to trigger some of those exploits. A good example of that would be MS 1180 uses this technique. Some of the newer ones have switched over to using reflectively loadable DLLs, so that would be another way you could call your foreign functions, but once again, you're back to compiling C code. And everybody want to write and compile C code? No, nobody really wants to do that. One guy. There's always that one guy. It's like, yes, I will write in C. You can still do that. It's all about the options, right? More options, more better. So at the core of it, these are the four functions that it actually provides. So that API is the number one that we're most interested in leveraging. So this is how we're actually able to tell it, please take this DLL, or in OS X's case, this dilib, this by this name, call this function, and we have all of these parameter types. So we have our in out, we have the values, or in the case of like the out parameters, we tell it the size that we're expecting. We pass all of that information into that Railgun API call, and on the remote side, it's going to handle all of that for us. It's going to make that call, and it's going to give us the return value, as well as it's going to give us a platform-specific error code. So in Windows, you're going to be having the result of that get last error. On Linux and OS X, you're going to use libc's error number, so you get that information back out. The last thing it does is it takes that error number and it uses the OS libraries to convert that into a string, so you actually have some useful information as a human, so you're not just like, I don't know what error 13 is, but it'll tell you like bad parameter or buffer size is insufficient, not enough parameter, or not enough permissions, what have you, things like that. So API multi, just like API. Like I mentioned, this is really slow interface, especially if you're over like a slower network connection, because for every single API call you're making, there's a transaction that goes from Metasploit to Meterpreter to make that API call. Now, you can make this a little bit faster if you necessarily don't need to act on the result of some of the functions. You can queue up like 3 or 4 or 5 API calls, and you can pass them all at once in one transaction using multi-API. So it's just a convenience function to make it a little bit more quick. After that, you have mem read and mem write. These ones are kind of like the process API the Meterpreter also has, but these are specific to the local process. That's going to be the one that Meterpreter is running in. These would be primarily useful if you're getting a structure of data back from, once again, from that example of like DNS query X. If there are like pointers in there to like, this is where the string is, or like this is where the IP is, or anything like that, you can use memread to easily read the information at that pointer, so you can just get that data right back out. So once again, like a convenience function, as opposed to having to use like the full-blown, heavier process API. All right, so the non-Windows implementations of Interpreter. Up until March of this year, Windows was the only interpreter that had access to this Railgun functionality. Since then, it's been added into Linux, and what I'm going to demonstrate for you today is the first demo of the OS X implementation of Railgun, and how we can use that. So pretty excited about that. So the mem read and the mem write calls are actually deceptively difficult. When you're porting this to different platforms, at the core of it, multi-API, the concepts can be applied to the different platforms, assuming that you can specify the different calling conventions. Windows almost always uses the standard calling convention, but Linux and OS X, it's cdecl, so it's not actually that bad. But the mem read and the mem write is very, very important and was deceptively difficult to implement. The reason why is because each Windows, Linux, and OS X, they all have different APIs that have different intrinsics within them. And the number one thing that's important about this is that we do not want our session to die if you try to read from an invalid address. Like, we've all made the mistake. Sometimes, like, a pointer just maybe it gets truncated, or you have, like, the wrong value, something along those lines. But if you pass in a bad pointer to mem read or write, you want it to fail gracefully and, like, return an error number to you and basically be like, try again. Because at this level, because we're working with the C API, Python can't handle those exceptions, so your session will die. It would straight up die, and that's no good. So on OS X, what we do is we actually use the mock APIs, and that'll return a nice error number to you saying that, hey, there's an invalid address there, or there's invalid permission. So we get a little bit better information as to why our mem read or write call failed, but the most important thing is it doesn't just segmentation fault and die, which is why we don't just directly use like mem read or like mem copy from Python, because that would definitely end up resulting in a segmentation fault, ultimately instability. So, no good. The error code as well is a little bit different from each one of the platforms. Like I mentioned, Windows, the entire like Railgun core functionality is over 5 years old now, I think. And like I mentioned, it was specific to Windows up until March of this year. And so a ton of it was very, very much specific to Windows. So the references are all like get last error and things like that. But libc on Linux and OS X can kind of be used to like the same effect. If a library has an error and it reports it through libc, we can still get the error information out that way. So we just kind of treat it as like get last error, and we can also retrieve the message that way. So that was also a bit of a different thing between like Linux and OS X, but for the most part, the mem read and the mem write were kind of the more complicated ones to implement. Most important thing. Can't stress it enough. If you read or write from a bad pointer, it's going to segmentation fault, and you're ultimately going to have your session closed out on you. So the mock VM read and writes are specific to the libc version on OS X. So we can use C types because we're already leveraging that quite a bit. But we have a little wrapper that dispatches the mem read and the mem write based on what platform the Python interpreter is running on. So if it's running on Linux, we're going to use process VM read and process VM write. Or if we're on OS X, we can use that mock VM read and that mock VM write. And the ultimate goal is that we're not going to have like a segmentation fault if we can't read or write from that. And of course, on Windows, I failed to mention that, but that's just going to use the debugging APIs of can't remember it, but like process open, and then you have write proc memory and read proc memory. That's it. But those ones are going to fail gracefully. All right, so now we're going to talk about like the actual details of doing it on OS X. So fewer pews here, and we're going to start to get into those segmentation faults that I tried so hard to avoid, but sometimes it's just inevitable. All right, so how the OS X APIs are all broken out. So turns out that like I got all like the C-type stuff working, and like you could load up like the .so files, call into the function, things like that. On OS X, not actually that useful, unfortunately. Most of the core API functionality that Apple provides for OS X is all in the dilibs in the framework, under that framework directory. So everything that you're used to dealing with from like social accounts, security, interactions with the system are all using these libraries here. And unfortunately, these are not straight C. So while we have the ability to call into like C functions, because these are not C, it's not safe to directly call into these. But we're gonna get around that, so never fear. Yep. So the foundation one right here, that top one, that's gonna be the one they're actually gonna use today. That's where the Apple script engine lives, and so these are all like the Objective C libraries. They're loadable via Python C types. There are some third-party libraries out there that allow wrapping these a little bit more easily, more cohesively. But in the context of like the Python interpreter, that is not an option because we can't be adding in third-party code. We can't rely on it being there. We can't package it up. It's just not feasible. So we have to do all of this natively by ourselves. Okay, so lib Objective-C. So this is the glue that allows like a native C application to load Objective-C runtimes. And so this is what we're actually going to use. So because we can call C native functions, we can load this library, and it's safe for us to load this and then leverage it to access those frameworks that we had talked about, like Core Foundation, the social framework, the security framework. Not very straightforward. There's also a ton of documentation on like why this is a bad idea. Apple does not really want you coding in C. If anyone has done like Apple or OS X systems programming, yeah, they don't advertise it. They don't want you to do that. They want you using Objective-C, Swift, things like that. So this isn't very well documented at all, and but you can do it. One important thing to note, though, is that because Apple doesn't really provide a whole lot of documentation around like libc and how it could be applied to their libraries, libc is actually a GNU project, so it is free and open source. So we can actually find much more documentation on this for like the Linux version of lib Objective-C. From my experience with just like the 3 functions they ended up having to use, it was all very, very accurate. The information was able to be carried straight over, so very good resource in that case. Now, the lib Objective-C provides a whole bunch of functions, but it actually came down to these 3 key functions that provided me with basically all of the interfaces that I need. And that was the ability to instantiate a class, so we can allocate and initialize a class, and then we're going to be able to call methods on that class to actually do useful things for us. And so just those 3 functions over and over and over again. Very, very repetitive, but with just those 3 functions, we can do this. So how Railgun actually ties into this is that we have the Railgun definitions for lib Objective-C, and then these are the 3 functions we're just going to be calling over and over again. And once again, very, very bad idea. Everyone's like, you shouldn't be calling into like the Objective-C libraries, but like, I do what I want. So worked out, not so bad. All right. But so how we actually have to initialize some of these classes, because the lib Objective-C stuff is all implemented in classes, and as anyone that's coded in C will tell you, it's got no class. This is how it rolls. But so the first thing, or like the main thing that you're going to be doing is going to be using this Objective-C message send. It's like the most important function. You're going to be using that to send messages onto the different objects. Unfortunately, something to note about this is that those first 2 parameters, that ID of self and the selector, those are always there, but that ... on the far right, this function is actually a cdecl function that takes a variable number of arguments. So that also kind of complicates calling things from Railgun, because Railgun, once again, having been primarily developed for Windows, Windows doesn't use cdecl a whole lot. It uses a standard call. If you're not familiar with the calling conventions, standard call has a fixed number of arguments about all the time. So there are a couple of exceptions like printf, things like that, where you can add on additional arguments, but for the most part, the function will always take X number of arguments. So message send, it's going to be a little bit more difficult. So what we're going to have to do is we're going to have to define the prototype for Railgun like over and over again, so that way we can apply it when we need to pass in the additional arguments. But that first argument there, that self, that's actually where like the class instance or the class reference object is going to be. Because once again, in C, like we don't have a concept of classes, so we have to pass in that reference as that first function. So that's how we do it. Okay, yep. All right, so the very first thing is that we use that get class function, so we can pass it in a class name. In the case of our demonstration of what we're going to do, we're going to pass it in ns apple script, and so that's going to get us a reference to that class, and then we're going to use the selector to call in the allocate and then initialize that, and we're just going to pass those ones in. All right, so this is very, very dry. One thing I forgot, this very first top line right here, is that prior to being able to use like get class and things on the from the Objective-C library, you have to load up the Objective-C library. That allows it to initialize itself, and it registers its class names, and at that point you can access them from lib Objective-C. So very dry. I didn't really want to point that out a little bit too much, but now it's time for the demonstration. So let's take a look at this. Right? Everybody knows the demo's going to be way better than like staring at that pseudocode. All right. Okay, so I am SSH'd into this MacBook right here, and I want to thank Tom McBee for loaning me his hardware to do all of this research. We're going to set up a Python interpreter payload. I'm setting a new option that's in this patch right now to fork to false. I'm going to talk about why that is in just a second. And public service announcement, if you did not know about the two-handler command, it's amazing. It's brand new within Metasploit pretty recently. Mind-blowing, right, Jeff? Aha! All right, so we got our session. Super elite hacking time now. Assuming I can type. Okay, so yep, got our Python interpreter session on our MacBook. And go background, use payload, or excuse me, use host admin OSX. Okay. So we're going to run a proof of concept script here real quick. And if we're really quiet, we're going to have it say, hello world BSides. I know it's cut off a little bit over there, but we're just issuing the say command. So in just a second, I'm going to ask everyone to be really, really quiet as this Mac screams out, hello world BSides. All right, show options, set, script. Always exploit. You guys ready? All right. Real quiet.
Hello, BSides.
Right there in the front row. And there we go. All right, so we have debugging statements because I absolutely love those all the time. But so as I've been talking about this NS Apple script, so we allocated and initialized a brand new class of that, but we initialized our Apple script from source because we read it off of this system right here, and that has to be passed in as not a C string, but like an NS string. So once again, like one of those libobjective objects. So we have to initialize that one as well. So we just so happen to do that one first, and that has a method where we can initialize it from a standard like null terminated C string. So that's how we do it through Railgun. And under the hood, this was really fast because we're both on the local area network, but like, unfortunately, if you were on a real network with any kind of like latency issues, it would be a bit slower. All right, so segmentation faults. So I had set that try to fork option to false. By default, the interpreters that are targeting platforms which support forking, they will do so. That's so that your exploit doesn't hang. It's going to fork the session into a brand new process, and then you can run your shenanigans from there from within like an isolated environment. Generally, as like a pen tester, that's what you want. You want it to fork a new process and set everything up there. So by default, that's how it's going to work. And still currently publicly, the Python interpreter will always try to fork when basically the fork system call is available. However, Apple, in their infinite wisdom, uses this thing called Grand Central Dispatch. That's what they refer to libdispatch as. And libdispatch is an inter-process communication mechanism used by a lot of the Apple programs, libraries, and things like that. In this case, the NS Apple script leverages libdispatch to receive events that were processed by the execution of the Apple script. When a process forks on OS X, libdispatch hooks that process and purposely corrupts itself. They do that so that the next call into libdispatch will cause a segmentation fault, and it'll cause the program to always crash reliably, so to speak. But to my knowledge, there's no way to reinitialize this. But what that ends up meaning is that if you follow what I've done here and you're using like libobjective-C and you're calling into these Apple libraries, if you have forked your process, If any of those interact with or somehow touch the libdispatch, your session is going to immediately die, unfortunately. One of the things I need to look into moving forward with this is to see if after forking there's a way to reinitialize libdispatch, that way you can leverage it without actually having it kill your process. And so all of this code is public. I really, really just like it when people show off like super cool stuff and they're like, oh yeah, this isn't done or something along those lines. Everything that I've shown, with the exception of the Apple script module, is all public under this branch right here. So if you do want to check it out, it's public right now, today. And I am hoping to get this wrapped up and submitted to the Metasway project as a formal pull request for review and ultimately acceptance in the next week or so. I'm hoping to get that submitted. But this is all actually done. I'm holding on to the Apple script because honestly, without forking, if you didn't fork ahead of time, then like you're going to kill your session. So I thought it'd probably be better to save people from that, unfortunately. But if you're interested in it, just let me know and I'll share it. But I don't really think it's something that belonged in there. I want to prevent people from shooting themselves in the foot. Got a couple of blogs out on the more of the technical details of how Railgun actually works. If you are more interested in that, there's that. Otherwise, I just want to say thank you for your time. And if anybody has any questions, I have some pretty cool bottle openers. And thanks, everyone.